ago did a talk on Reynolds stuff, but I don't remember it anymore. But I do remember things like the identity lemma and some of the other things factoring into it. So don't know how much of that. Oh, so still, yeah, how much of that we need to know ahead of time in order to understand it. But yeah, well, we'll see how it goes. Hey, hi, Sergey.
Hello. So, sorry, I didn't want to interrupt. You were saying something?
I'm done, I think.
We're just talking about the paper that we were proposing reading for next time, the parametricity for primitive nested types and GADTs.
Right. I wanted to make a comment about your what Adrian was saying last meeting, in the beginning of last meeting, about filterables and partitionables, but maybe let's skip this to a minimum. Would you like to try to? So just very quickly, okay, so here's the thing. So you were proposing something like partition, which goes from predicate. So I'm just going to gloss over some details, right? And then f of a and to f of a times f of a, right?
Right.
Now, and then you have unpartitioned, which was supposed to go in the opposite direction from f of bool to f of a to f of a, or maybe it was across here, I forgot. To f of a, right?
Right.
Or so, and then I'm omitting some dependent type stuff here, which you had. Now, one immediate issue here. So on the surface, it looks reasonable. So you can define like this, and there will be some functors f with these properties, but they will not be the same as filterable. And there is a technical, maybe you can solve this technical problem, but there's a technical problem with this formulation. And the problem is in this part of the type signature. Because this part of the type signature, kind of it's telling you that the functor f must be applicative. You can take two f's and you can merge them into one, which is a typical for applicative. So applicative kind of, it has a zip operation, which is f of a, f of b, f of a times b. And now you don't have f of a times b here. You just have the same type a. But this is similar. You're taking two of these, and you're merging them into one. So you have two containers that you kind of merge element-wise in some way, or even with this using this one here. So the intuition here is based on the intuition of a collection, which is that you you have elements and you can have order due to the structure of the collection, and so you can kind of say which element corresponds to which other element in a different collection, so you can zip them together in some way.
Yes.
Now this is so this is certainly so okay, so this is fine for polynomial functors because all polynomial functors are applicative. So all polynomial functors will have the zip operation, and then you can probably define, if they're filterable, you can probably define partition and unpartition, which so in order to approach this using the method that I'm using in my book, I have so you can do this. You can ask, so if F is partitionable and G is partitionable, what about the product F times G? What about the coproduct F plus G? What about something else, like a function from something to F, maybe, and so on. So what will be their properties? Can you also define partition and unpartition for those? And you will find that you cannot do that for certain constructions, because I believe so. Here's and let me just be brief here, and let me just say there is a specific counterexample that you can take a look at, and I will just conclude with this counterexample and a very brief intuition about it. So counterexample is that is a functor which is not applicative, but filterable. So what I'm saying is that your unpartitioned function kind of assumes that the functor is applicative, because it kind of has this shape where you have several F's and you merge them into one.
Right. I can certainly believe that because it's clear that partitionable is a stronger constraint than filterable. There are every partitionable ought to be filterable, but not the other way around.
Okay. But what you were trying to eliminate is this kind of gratuitous deletion of elements, right? So that filterable that doesn't delete unless it is strictly necessary. That's
Right.
what you're trying to do, right?
And trying to approach a definition of conservative filtering.
Right. Now, there might be a problem with this, but here's a counterexample. Let's take some fixed types P and Q, and let's do the following. So the coproduct of this and this, now by themselves, each of them are filterable, and I believe also partitionable. Now, so what does this kind of thing do? It's just a function from a fixed type to an option of A, or maybe A, right? Now, this is filterable because if A does not pass the test, then you can always return 1 for a given value of type P. You can always first compute this function, and then see if A passes the predicate. If it does not, then you just return 1. If it does, you return A. So it's like saying, first you take this function, and this is a maybe, and then maybe is filterable. So you apply filter to the maybe. Or maybe perhaps more kind of clean. Let's take G of H that are filterable. Right. And then let's take this now, or maybe even, yeah, anyway, let's do that. So in any case, this functor is not applicative. And the reason it is not applicative is that is this coproduct here. Because you're supposed to put together FA, FB, and get F and A times B. Now, FA could be all on the left, and FB could be all on the right. You cannot put them together. P and Q are completely unrelated types, so you cannot put them together. So P and Q could be types with different cardinality. So, and we don't even know how to compare them maybe in cardinality. And so there's no way for you to produce either from two of these. You cannot kind of string them together always in general. Now, however, if these two are obtained from partition, then they won't be just arbitrary values of type f of a. They will have the same structure. So for example, if f is on the left, you filter it, right? It will always be all on the left here and always on the left here. And that's not a problem then to put them together. So this is kind of a weird situation where you cannot implement this type signature, but you don't have to actually implement this type signature. You need to put together only those pairs of f that come out of here. And those are not general pairs of f. This is actually a smaller type than the pair of two f's. But you did not describe that smaller type in any way.
Well, you can describe it at least partly.
So what I'm saying is that if you describe that type more precisely, that this output here is not actually just a pair of arbitrary f of a's,
right?
But they have kind of they come from filtering out of the same structure. Now I don't know how to describe that. I'm just saying you have to do it, because if you don't do it, then you're losing the possibility of putting back together the pair of f of a's into a single f of a, which you don't always know how to do. Like suppose that, okay, that this function, I just gave you an example of this function, right? Because it's just a kind of a simple example. But suppose I just say you have a partitionable functor g and the partitionable functor h, and you want to consider a coproduct g plus h. You'll have exactly the same problem. You are going to give me a pair which will, on the surface, will be a pair of g plus h times g plus h, but that's not true. It's actually going to be g plus g plus g times g plus h times h. But you don't know that because you write the type signature in this way. And if you wrote it in a better way somehow, which I don't know how, then you would certainly be in a much better position to prove that the coproduct of two partitionable functors is again partitionable. The coproduct of two filterable functors is filterable. That's pretty easy. Should be just as easy for partitionable. So there's this kind of technical problem, which I just described. And if you can solve this problem, then certainly you can have a much wider class of partitionable, which would correspond more closely to filterable.
Yes, I wouldn't expect it to correspond exactly.
Maybe not. No, certainly not. I mean, you are just saying you just say, well, filterables that lose information, they will not be partitionable. That's good.
Yes.
So we want that. But we don't want to accidentally lose filterables that don't lose information, but they're just made of a coproduct, and you don't know how to deal with this because your type signature is somehow too general and it doesn't describe that situation well enough. So that's all. Anyway, that's what I wanted to say.
Mhm.
Yeah. So this example of a non-applicative function. So this is filterable, but this is not applicative.
Mhm.
It's just an example that's on my mind because in the chapter about applicatives, I give counterexamples for what is not applicative. It's actually not so easy to find something that's not applicative. And this is one of the easiest examples, actually. So, yeah.
So wait,
Anyway.
so I have a question.
Yeah.
I've been trying to refresh my memory just now about the definitions of applicative, and I don't see anything about zip.
Yeah, because they don't know how to do it in a pedagogical way. So I'm doing it. A zip function is much easier to think about. It's much more familiar to programmers. You know, you zip two lists together, you get a list of pairs. Applicative functors are defined in most other tutorials using different methods, which is very difficult to think about.
Are you saying that is this a equivalent to the usual notion of applicative?
Yeah, except, well, it has to be pointed. So there, I still need the
Pure,
function,
yeah.
a pure. Yeah, I need a pure for this, or some kind of unit. So I need an I need an f of 1, a value of type f of 1. But the other method in applicative is usually it's this app, which is like f a to b, f a, f b, and even the laws for this method are very hard to write down. It's a very inconvenient starting point, and it's very inconvenient function for proving things about, because its laws are so complicated, and it's kind of very unintuitive of why this is equivalent to other things. So in any case, I mean, this is the only positive side about this function is that it gives you a better connection to category theory. Because with this function, you say, well, okay, so this obviously, this is the type of morphisms in some category. And this is a type of morphisms in another category. And now we're having a functor between these two categories, which maps morphisms to morphisms. And well, great. Now let's now write down the definitions of category, definitions of functor, and check the laws. And if you do that, then you get the correct laws of applicative. But this is far from obvious, right? That's what I'm saying, is that like if this is a type of morphisms in some category, it means you need a morphism composition in that category. So you need to compose two of these. And so you need f of a to b going to f of b to c, going to f of a to c. So you need this function now. Very complicated. Now you can certainly define this function using app. But that will be kind of an ugly, complicated code. I do some of this in my chapter on applicatives. And so I do derive the equivalence, but actually, so this, for example, this will be a composition law for morphisms of this type. And then you need associativity for this composition, right? And that's, so associativity is going to be a law for this function, which is going to be big, ugly law when you express it through app. it's not going to look anymore like a composition law. It will look very strange and complicated. Here it's kind of clear. You're doing composition of morphisms, so it needs to be associative, and then you know how to write associativity law. And here you don't. It's not clear what is to be written, what kind of law. Anyway, but so this is
it's coming up in the next chapter, you're saying.
yeah, it's what I'm saying is that this, starting to define applicatives using this is kind of a bad idea pedagogically. You can start from category, like from here, or you can start from here, which is very far from category theory, but close to programming, close to practice. Because in practice, you often use this function. And the laws of zip are much easier to understand. And also, there's associativity, identity. So it's kind of monoid-like operation. If you have f1, this f of 1, if you put it here, then it will be f of 1 times b. So that should be identity. Well, it just falls out. And associativity, f of a, f of b, f of c. And then f that maps into f of a times b times c. Associativity of product is there, and so it's kind of easier to think about in this way what the laws of this must be. So yeah, it's equivalent.
I have a question.
Yes.
Question regarding the type. Okay, you define AP as a type from f of a arrow b arrow f of a f of b.
AP is a specific function of that type.
Okay, the middle arrow, I guess I'm just kind of wondering what category or what is AP defined in? Is the arrow in the middle an actual arrow in some category, or are we saying that there is an isomorphism between the f of a arrow b and f of a arrow f of b?
So first of all, these are just function arrows. So right, if you don't, first of all those categories are defined on top of the usual category of types and functions. So the first step is to look at this as a normal type signature of a function, higher order function. So all these arrows are just function arrows. And then you say, okay, well, this looks suspiciously like a function between this and that.
Mm-hmm.
Right? And both of those look suspiciously like morphisms in some categories.
Mm-hmm.
So now let's take a look at that and let's try to define those categories and to check if that's true, if those are morphisms. And then this function from this morphism to this morphism looks like the functor mapping that's supposed to map morphisms to morphisms. So this arrow is then this arrow is no longer just a function, just an arrow in a category. This is a mapping between morphisms and morphisms. So you need mapping between objects and objects in a category, and you need a mapping between morphisms and morphisms. And so this looks like that mapping now.
Yeah.
Are the two categories the same?
Well, no, because the categories have morphisms that are very different.
Okay.
So it's not an isomorphism by any chance. They're not going to be the same categories. So the objects of these categories are also different. So here the objects are just A, B, and here objects are f of A, f of B. And so the objects are, so you map object A into object f of A, and then you map this morphism into this morphism using this function app. And so then you say, okay, well, if it's the part of a functor between these two, then the functor must satisfy the axioms of a functor. It must map identity to identity, and it must map composition to composition. Is
Mhm.
that true? So then you
Mm.
have another bunch of laws to verify.
Mm.
What is identity here? Well, it is clearly this what is it? This f of 1, right? The pure of identity. That's the identity on the left. Now you need to check that this pure is mapped into pure of identity is mapped into identity. Okay. And then you have composition also. You have this kind of composition operation for these morphisms. For these morphisms, it is an ordinary composition of functions. And then you have to check that the composition on the left is mapped by app into a composition on the right. And then you have verified that you actually have a lawful functor between these two categories. Provided that you already verified that this satisfies the associativity law. Anyway, this is a lot of checking here, which is kind of a lot of laws that you have to write down and check, and they're not easy. And here there are very few laws that you can write down and check much easier. And then they're actually equivalent. And I believe I prove all of that step by step, all that. I did not necessarily write out all those laws, but I prove the equivalence from that back to here.
Okay, just to make things a little bit more concrete, in your definition of AP, the A arrow B, we are picking a particular F, right? A particular arrow, right?
No, this is
No?
a type. This is a type.
So the functor F is applied to the type A arrow
Yes.
B,
Yes, yes.
not an arrow F from A
no,
to B.
uh,
Okay,
no,
I'm a little bit
no,
confused here
no.
then.
This is a type, right? So in Scala, you would write like this.
But I wasn't, okay, so functor F is from types to types now.
Yes.
That's
No,
why I was
functor F is from types to types. Yes.
that's why I was confused. The A arrow B is not the same as the arrow in the middle, right?
Well, like I said,
Okay. Now,
initially you
using
look
the
at
double arrow
Scala,
makes more sense. Okay.
initially looking at the Scala type signature or equivalent Haskell type signature, it will be just the same arrow everywhere. So this is a type. This is not a specific function of this type. It's a type. So
Okay.
and this is also a type. So this is a type, which is, for example, if f is a list, then this is a list of functions. And this is a function from one list to another.
Mm-hmm.
Or maybe more easily, if you think of F as being maybe, do we have an AP for that? Okay, well, if we have a maybe function, if we have a maybe function from A to B, and we have a maybe A, and we can like apply those things.
Yes. If
both
maybes are not empty, then you can apply that function to that value, and you get a non-empty maybe as a result. So anyway, this is in the applicative chapter, but I mean, this is certainly not trivial, and I would like to, so Jongila, did I answer your question?
You've at least made the notation clearer. Yeah.
Okay.
Thanks.
Because this is, I mean, this is this is a starting point in most tutorials about applicative functors. Or maybe these not functions that they denote like this and like this and like this, and this is just this is not what I do in my book. My book actually departs from accepted practice in many ways, from the usual ways that things are introduced. So this
Well,
is
that's
one.
good, because I always found those notations to be,
Yeah, well, people, in my view, people
what
don't.
the hell is that mean?
Yeah, people don't make the effort of going back and asking, well, what would have been a better notation? What would have been a better starting point? What would have been a better word to use to describe something? And this is not something that everybody would like to do, and this is not something like, for example, semi-monads, right? Semi-monads. I don't know. I don't care if this is accepted or not. But what I found is that going back to the monads, right? What I found is that the for yield notation or the do notation in Haskell do not actually depend on the pure method of the monad. They are, so Scala kind of incorporates the pure method by default, but you can use that the for yield notation or the do notation with data structures that do not have the pure method, that just have the flat map or the bind, and that's just as fine. As if you don't need the pure method, you don't have to use it. The code will just work as long as the flat map is associative. So then everything is fine. And that, I mean, this is one of the first things that I realized, that actually we have been working with semi-monads all this time, not with monads. Monads are are smaller than semi-monads. They're more constrained. They have more structure. They have better behavior. But we haven't been actually using them so much in the code. Some code does, certainly, but in many cases, you can get away with a semi-monad just as well.
If your do notation has something like a return in it, is that when you use pure?
Yes. Return is a method that is the same as pure in Scala. And return means that you have a monad, full monad, not just a semi-monad. So semi-monad does not have return. It has the bind, but it does not, and it has the associativity. Well, it's just the same as a semi-group. Semi-group has the combine operation in the associativity wall, but it does not have a unit. And semi-groups are useful. Maybe in most cases, you actually have a monoid, not just a semi-group, but why worry about it? So in any case, that's my comment about semi-monads. Unfortunately, I had very little time these 2 weeks to review the previous session, the recording that I made. So I apologize, but I have no other comments at this time about the previous session. Anyway, so this is how far I got. So there was some question about semi-monads and why I'm talking about semi-monads, and that's anyway. So, let's please continue from the point where you stopped. I don't know at what point you stopped. I will still have to go back to the recording.
We got to the end of section 10.1, I believe. So that would be means starting at the beginning of section 10.2. So basically 10.1 covered a bunch of examples of semi-monads. Do you have any full monads that where we were actually taking advantage of the fact that they were full monads?
Yeah, well, most of them are full monads.
Most
yeah.
of them are full monads. Are we were we doing anything with that?
Well, I mean,
Right. Yes.
this is not very, most of the time you don't care that they're full monads. I mean,
Right.
most of the time you just use the flat map method.
Yes. But I do see at least one call to pure in one of your examples. So,
Sure. And this-
yes. So
certainly,
a bunch of examples of monads and semi-monads. And so
Right.
section 2 talks about the laws. And what are the laws? Why do they hold?
Yeah, don't we need the identity when we do things like fold or reduce
Yeah,
in general? Granted, you don't have to do reduce all, I mean, you don't do reduce all the time, but flat
Well-
map is sufficient for
well,
many
reduce is not a
cases.
monad operation, right? Reduce is not an operation of a monad.
Right.
oh, it's monoid, yeah.
Monoid, I'm sorry, monoid,
Yes.
okay.
Yeah, I mean, that's true. So, I mean, reduce. So, if all your sequences are always not empty, then you don't need the unit when you do reduce.
Right.
So, having an empty sequence is a nice convenience, especially for formal proofs and reasoning, but it's in practice, you don't always need it. In practice, often you don't need it. You don't need a unit. Actually,
Yeah, I mean,
yeah.
in practice, we always do a check, right? We check if it's something is empty or not.
Yes.
And
Well,
we
you
take
see,
a different
so,
logic.
Yeah. So, I mean, in practice, almost everything has a unit if you look hard enough for it. But you don't always use it. It's just in practice, all types are monoids. Actually, I have somewhere I have an example or an exercise to prove that. All types that you can write down concretely without type parameters are monoids. Whatever you write, list, array, string, int, boolean, float, whatever. Well, float, you can argue it's not a monoid because floating point operations are defined violating associativity law. And you can say, well, it's not a monoid, but at least it has the appearance of being a monoid. Anyway, so similarly to that, almost all monads almost all semi-monads are actually full monads. There are some examples where this is not true, like semigroups that cannot be made into a monoid, and semi-monads that cannot be made into a monad. They're relatively rare and practically not very important.
I had a question about the laws of flatten.
Yeah.
Let me see if I can get there. Yeah, so the laws of flatten. I was kind of interested in the notion of the type, that the types are equivalent rather
Mm.
than, it seems like you're interdefining flatten and flat map, and I sort of
Yes.
get that, but if you're saying that one type is equivalent to another, doesn't that mean that you have to be able to take any instance of one type and turn it into an instance of the other type? You
Correct.
can't just say, okay, I'm going to take flatten and move that. Oh, where'd you go? And move
That's
that
correct.
over.
That's good. Yes, that's correct.
Um,
So that is actually, yes, it is not just that I'm saying that, for example, the flatten method of a list is equivalent to the flat map method of a list as defined in the standard library. That's not just what I'm saying. Exactly as you described, I'm saying that the entire type of functions of this method, of this type signature, is equivalent to entire type of the methods with flat maps signature that satisfy additionally naturality law. Now, this is yeah,
okay.
this is more than just by coincidence. For the standard library, certain methods are expressed through each other in this way. No, and so you see, I express one through the other, but it's not enough to just express one from the other. I have to do the round trip in both directions and show that it is from one I get the other and then back the first one and vice versa. See that? So this proof is in two parts, where first I start from some arbitrary function flatten. At this
Is
point,
that the F here?
FTN, no,
Oh, okay.
no. So
So
then,
FTN is not necessarily flatten. It's any function with that
well,
signature.
it's any function of that signature, yes. Then I define
Okay.
the function with signature of flat map. And then I define again a function with signature of flatten,
Okay.
which is flatten prime. And then I want to prove that flatten prime is the same as flatten. So, and then
Okay. I think I get it. So this like FTN is really more like a variable that's
yes,
some instance of that type. It's not the actual flattened function,
no, not
which
for
is what was
any
confusing
specific.
me.
Okay, well, this is a bit confusing because we're talking about some specific S, right? The functor S, of which we are defining. We're trying to define monad law for that. Or we're trying to define methods, flat map and flatten for that, right? But before we define that, we already know that all possible functions of this type signature will be equivalent to all possible functions of the other type signature. So,
Okay,
so you see that. So this is, yeah, this is a little subtle, and I want to make it very clear that this is not just a specific function that happens to be expressed through another specific function, because that is not really very important. I mean, I just say, well, 5 is expressed as 10 divided by 2, so 5 is equivalent to 10. 10 is expressed as 5 times 2. So 5 and 10 are expressed through each other, and so they're equivalent. This is nonsense. This is just, this doesn't mean anything, right? 5 is equal to 10 divided by 2, correct? This is just an accident. You can express it in all kinds of ways. It doesn't mean anything. It doesn't mean that 5 is equivalent to 10. That's nonsense. 5 is not
Would it-
equivalent to 10 in any way.
Would it be fair to say that you're saying that the flatten as a type class is equivalent to flat map as a type class?
Yes, you can do that, but this is a weaker statement. So that, in fact, The statement is that any function of this type signature, whether it satisfies the laws of flatten or not, right? Any function of the type signature S of A to S of A is equivalent.
That satisfies the left naturality law.
Well, the left naturality is for the flat map.
Oh, okay,
This
so
one
that's
doesn't-
going the other
this-
direction.
Yes, this doesn't even need to have any laws at all. Any
Hmm.
function of this type signature doesn't have to satisfy any laws whatsoever. It doesn't even have to be a natural transformation. It's still equivalent to some function of the type signature of flat map that satisfies the left neutrality law. And that flat map only has to satisfy the left neutrality law and no other. It could be violating every other law. We don't care at this point. So this is a very kind of narrow and weak statement, which explains what it means that when people say often that, you know, flatten is equivalent to flat map, or, you know, you can define monad using unit and bind in Haskell, or you can define the monad using unit and join, and it's equivalent. So what does it mean it's equivalent? Well, this is what it means. Actually, any function of one type signature has a one-to-one correspondence with some function of the other type signature. So even before we start talking about other laws that we impose, there's this equivalent. And in fact, this equivalence is an instance of the Unida lemma. Natural transformations of certain kind are equivalent to a different type. So at this point, I don't yet have Unida lemma in my book, so I don't want to talk about it. But essentially, that's what it is. Maybe I could throw away all these proofs, I don't know. But it's not a big deal.
All right, I'm gonna have to think about that.
I mean, this is just you know, if you take these functions, one of them has, so flatten has one type parameter and flatmap has two type parameters, right?
Right.
It's impossible that a function with one type parameter is somehow equivalent to a function with two type parameters. It's just impossible. Where do you get this second type parameter? You know, what do you do with the freedom of choosing the second type parameter? So, but this is not true that they're equivalent. It's equivalent as long as there is a neutrality law. So this neutrality law kills the freedom of choosing one of the type parameters. So flatmap has two type parameters, but it satisfies the neutrality law. So actually, it does not have so much freedom. The Unida lemma tells you that. So the Unida lemma tells you that natural transformations of certain form are all those natural transformations as a type of natural transformation is equivalent to a different type that doesn't have any functions. It doesn't have any type parameter corresponding to those natural transformations. So this is an instance of that, but this is reasonably easy to prove. So why not? Why not?
The left naturality law actually has three type parameters in it. So
yes, right. It just tells you that you can change one of the type parameters arbitrarily. So you have parameters A and B. You can change A arbitrarily. So for example, you can set it equal to B. You are constrained sufficiently that you won't lose any expressive power by doing that, and then you get a function with just one type parameter. So that is basically what Unida lemma tells you, and this is a specific instance of it.
okay.
Anyway, naturality law. I'm writing this all out like in in great detail, just so that it's clear. Let me maybe make it a little even more clear. 10.2.2.1. Type of function.
I would suggest maybe instead of, when you're mapping from one to the other, just use some other something other than like FTN as being the arbitrary function in that type. You know what I'm saying?
Yeah, I can just use P and Q instead of that.
Yeah, something like that.
Yeah, I could do that.
That would have probably gotten me, because I kept thinking you meant the flattens or whatever. Yeah.
Yeah, this is a bit, okay. Yeah, you're right. This is a bit confusing.
Okay. I had another question.
Hmm.
And I think you kind of go into it in this section, but where is it? Page 383. Yeah, okay. That the product, given two semi-monads, their product is a semi-monad, and if they're monads, then their product is a monad.
Yes.
And the thing that I started thinking about was, some monads sort of are more like they have runners, right? You sort of have the monad and then you have to do something to it to get the data out, whereas other ones are more more like they don't have runners. Instead they sort of have a value that comes out, and then I guess maybe you have to extract things out. And so when you take the product of them, what happens? Do you still have a runner that, or do you extract? It's sort of like,
Well, so
or do you just treat the two side?
I'm not sure I follow your logic. So what is the difference between running and extracting? So why is extracting not some kind of running? So here, my comment would be that some monads don't have runners that extract a single value, and others do. And sometimes, for example, the list monad, you cannot extract a single value out of it. List could be empty, or it could have many values. So which one do you extract? And or maybe monad, maybe it's empty. So what value can you extract? You cannot extract. Instead of that, you can run it.
Well, you're sort of and list, you're generating
but what you can do
a
instead,
list out of a bunch of pieces that create lists, and
yes,
kind of put them all together.
But you can say, for example, that a runner sometimes will transform into a different monad. Let's say you try to extract the value, but if you don't have a value because the list is empty, then you throw an exception. And so that means you are now in a different monad. You are in a tri-monad in Scala. Or you're in either monad, say. Or you say, I'm interested in extracting many possible solutions at once for some search problem. And so I'm really interested in getting a list of results out of whatever monads you have. So you have a runner from your monad into a list monad, and it could be empty or it could be non-empty. So that is, so in other words, so I distinguish between runners that are morphisms from your monad into an identity monad, which just extract a single value and always extract a single value. And runners that map into a different monad that sometimes can, could be a pass-fail monad, or it could be some other. So, so a typical situation is, imagine you have a monad that is a tree, some kind of expression tree, and you evaluate that expression tree. And the result could be a single value, or the result could be failure to evaluate. And so then it would be natural to run into either monad. But what if you never fail because you're evaluating some kind of pure lambda calculus? Then it would be reasonable to evaluate into a single value always. So in any case, so that for the product, you can derive the runner. Now, how do you derive the runner? Well, clearly, it's a product of two runners, and then you get a product of two values in the end. So this is not, you're not running into an identity monad, clearly. You're running into a product, which you can then try to collapse into a single value, but this is not. So what I'm saying is that it is not obvious how to define a runner for the product. You might be able to define it in certain cases. Imagine that you have two list monads. You have a product of them, and so then you have two lists as a result. So how do you extract a value out of them? This is application specific. You might be able to do it, or you might be able to extract a single value, or maybe something else. But in any case,
Yeah, I mean, in that case, you're getting out a product, a pair of lists, and that's kind of what you kind of expect from a product.
Yes, yes, but you see, I'm making a point by emphasizing this thing about runners. I'm making a point that in practice, you always need to extract values out of a monad in some way. In practice, your monad value is not the end result of your program, and you have to do something with it. Maybe run the effects or whatever, and that is the running operation. So it is important for practice. It always needs to be done. You cannot just.
But it seems like for something like list, I mean, it's the list that I want, right? I'm doing like some for comprehension to loop over a bunch of lists and combine them together. And
yes, maybe that's what you want. This is application specific. So
okay.
in some cases, what you want is the entire list of values. In some cases, you aggregate it in some way. In some cases, you want to know if it's empty or not. And so on. It's application specific. But yeah, so what I'm saying is that in some cases, list monad is what you want. But for things like state monad, continuation monad, and lazy evaluation monad, other such things, that's not what you want. Those data structures are not here the end result that you want, and you need to do something to them to extract the results that you want. So that is,
and that's why it was a little confusing to me that you could just pair them together, and because you have one that you need to run to get the effects to happen. The other one, maybe you actually want the data itself, and you pair them together, and it's like now you can't run it or extract.
No, but I did not say what to do. I don't know what to do. I mean, this is application specific.
You're just saying that you can combine the flattened methods.
You can combine the methods and the laws hold.
Okay.
So whatever you do with the resulting monad, I don't know at this point. So this is maybe application specific. It is not trivial that you can do those things. For example, co-product does not work for monads. Cannot combine two monads with a co-product and get a new monad. Coproduct only works in one case where you combine some monad M with the identity monad. So coproduct A plus
The
M
plus
of
of those. Mhm.
A plus M of A, only that works in general.
Mm.
But M of A plus N of A does not work.
Mhm.
Actually, at the beginning of our meetup today, I was giving you an example of this kind where a coproduct is not even applicative. So it's not a monad. So yeah, so the product construction works. The runners are not obvious how you can run the resulting monad.
Mhm.
But
I mean, it seems like you go into that some in this section, right?
yes, but in many ways, so sometimes in many cases you want just to extract a single value because your monad is kind of effect that simulates some kind of effects, and those effects are external to a single value that you're computing with. Like the state monad, it changes some state somewhere, but there is a single value that you're computing with, or a continuation monad, something like that. But so for those monads, you want to have a runner to the identity monad, so M of A to A. But in other cases, this would not be what you want, or this would not even exist. And those other cases are the maybe monad, the list monad, of the kind that you say that they're just data that you get.
Right.
The either monad, you cannot map either monad into an identity. So
Right.
this, I talk about this here.
And then you start getting into like, yeah, where you have the target
Yes.
is another monad, right?
Yes.
Which
And
then is more
yes. So this
cleaner, I
is
guess, in terms of extracting.
so this is application specific. So sometimes you
Okay.
want that, sometimes you don't care about errors. You just want to know if you have a result or not. And sometimes you do care about errors, and sometimes you want to find all possible results, not just one, and so on. Anyway, that's
So
let me
that
check.
kind of reminded me of another question I had,
Yes.
sort of going back to what we were talking about at the beginning. A lot of times when you see monads defined, they say, oh, you have like functor and then applicative, and then you have monad or something like that, so you sort of need to be an applicative in order to be a monad. But do monads actually use like that app function that you were describing?
No.
It's really just the pure that they want, that they
Yes.
need.
Yes.
Okay.
No, they don't need to be applicative, and in fact, they don't have to be compatible. I mean, this is a completely arbitrary decision. If you want to say that the monad needs to be compatible with the applicative that you're using in the same program. And there are often more than one applicative implementation for a given data structure. And you might use different implementations. So zip could be implemented in different ways. And also monad can be implemented in different ways for the same data structure. And you might use those different ways in different places. So they don't have to be compatible. So there's one thing there, which is if you have a monad, then you can derive app from it. So you can derive app from flat map. But it's not an equivalence. So if you have flat map and it satisfies the laws, then you can define app that satisfies the laws, or zip. But not the other way around. So it means that if you have a chosen monad structure, then you also can induce a chosen applicative structure. But that's all. So there might be many other monad structures, many other applicative structures, which you may prefer to use for specific program, which do not follow. So this zip you can use that does not follow from flat map. And an example, trivially from Scala, is that the standard zip function that you use for lists and the standard flat map function that you use for lists are not equivalent. They don't follow. So the zip does not follow from the flat map.
Because the standard zip will throw away information if one list ends early. Is that part of it?
Yes, so that's part of it, but also, yeah, that's part of it. But even this is even worse. I mean, if you derive zip from flat map for lists, then zip will generate a list of all pairs from one element from first list, one element from second list. It will not generate a list of corresponding pairs. It will generate a list of all possible pairs. And
yeah, okay, I see what you're saying. The normal one is that it would do the corresponding pair.
That's right.
Right.
So that kind of list is an applicative structure that you want most of the time. And it is in the standard library for that reason. But it is not derived from the flat map. And there's no reason to expect that it should be. These are completely different use cases. So you use zip for different reasons than you use flat map. There's no reason to expect that you should be able to always derive one from the other in this rigid way. So, yeah, but you need to keep in mind that, yes, theoretically speaking, if you have a flat map and you always can derive the corresponding zip, corresponding app.
Right.
And so, well, yeah. So
yeah.
it is not always clear how to define those things, and so that's why I'm going through all kinds of cases and all kinds of type constructions that tell you how to define monad methods and so on.
So what I hear you saying is that, like, for a given functor, like we'll sort of say, like, hey, you know, list is a functor and maybe it's an applicative and it's a monad, but that kind of implies a uniqueness of the monad. And you're saying that that's not really the case. You could have a list or a given functor and have different monads on it.
List has two monad structures, as far as I know, and more, at least two applicative structures.
What are the two?
Well, I put it. So I think it is somewhere in this chapter at least.
Okay. Yeah.
Well, I'm not sure which version of PDF it has. I've added it fairly late. It might not be in the version that you have, but
Okay.
the standard one, the flatten that just flattens all the nested lists, is the standard one. But then there's another one where if even one of the nested lists is empty, then the entire result is empty. It's kind of very, very demanding in terms of non-emptiness, or greedy or something. So if all the sublists are non-empty, then you concatenate them. But if at least one of them is empty, then the result is an empty list. That is the flatten function. It satisfies all the laws. And I don't think there's any other implementation that satisfies the laws. And also applicatives. So there are at least two different applicatives. The usual one, which collates corresponding elements of the list, and the one that's derived from flat map, which will give you lists of pairs. But actually, there are two different flat maps, so you can derive two different zips from it as well, which will have different behavior for in certain cases, maybe.
Okay.
Although I'm not sure. If one of the lists is empty, what do? You return an empty list. There's not much else you can do. So I don't think you can actually have different zips coming from the two different point maps. So, but anyway, so yeah, so that's let me check on my kid actually, but please continue.
Yes, I guess the applicative chapter is the next one, so it's starting to sound as if that's more and more interesting.
Yeah.
So let's see. Do we want to go through more of these proofs? Do we want to go through the instructions on the various types of things that can be monads and semi-monads? Do we want to jump right to the further developments? I guess my what did I think was, I mean, one thing we might want to do is look at section 10.2.6, the monad laws in terms of Kleisli functions, in case anybody isn't familiar with that formulation, which is particularly elegant.
Okay.
Should I share, or Pete, do you happen to have the section 10.2.6 handy?
Yeah. Okay, again, my putting the stuff on top. Okay, let's get rid of that. Yeah, so monad laws in turn. This is it, right?
Right.
Yeah, right. So the Kleisli functions look like that. Well, yeah.
Right.
And then you can combine them using this operator, which I think I've also seen as people call a fish operator or something like that. But right. So go ahead, you talk.
I guess I don't have, I think we've looked at Kleisli composition in the category theoretical context before. So it's just, this is what it looks like in the programming context. You've got basically it's an A to B to B to C to A to C, which sounds like normal composition, except that as Sergey would say, it's twisted by putting the right-hand thing after each arrow into a monad. But so that gives you a very concise way of expressing a number of these laws. As we see on the next page here, statement 10.2.6.1. So pure after F in Kleisli is F, and F after pure is F.
Very
That's
clean.
Yeah.
So what kind of structure does this give us? Is there's I remember the Kleisli term, but I don't remember much about the concept. Does it form another monad starting from this monad?
I don't think it forms a different monad. But it's a notation for what's the word? It's a way of thinking about the types of monadic operations that is maybe more straightforward.
Yeah, it's the same monad, but you're just sort of defining it. You know, so it's defined in terms of, you know, the flat map of the other monad. And in fact, you can go back and forth. So there's sort of equivalent expressions of monads. But doing it this way gives you these nice, clean kind of laws, whereas, you know, before it's more like, oh, you have to F map the pure across the thing to get, you know, stuff like that. So these laws tend to be cleaner, right? That's the identity, and composition just looks like almost like function composition, right? It's just, or association. Dissociativity law is just kind of like the regular one. So I think that's, yeah, so they're cleaner, and I think that's partly why Kleisli invented all this stuff in the first place. That would be my guess, is that he was trying to figure out how to get these kinds of things to work together cleanly. And this is how it works. And it's interesting because I think when we were first looking at category theory, you know, I was always thinking, oh, well, you know, you have the types and functions category. And so if I've got type A and type B, then it has to be the functions from A to B. That's, you know, that's what the category has to be. But then, you know, Sergey said, well, no, you could have the arrows be an arrow from A to B being a function from A to M of B for some functor M. And I'm like, that kind of opened up my thinking about categories, that there's lots. It was way more general than I thought. So anyway, that's just a little historical.
Even if
note.
you're only talking about categories in the context of a programming language, yeah, there are definitely more options than just the vanilla Hask category.
Mhm.
So, and then in the next section, Sergey talks about a trick that you can use with using the Kleisli notation. But
I didn't quite work through that. Can you
Yeah,
summarize it?
I didn't either. I can't summarize it except to say that, oh, that looks like a clever trick, but
Yeah.
yeah.
I guess we lost Sergey here, huh?
Mhm.
Right. So yeah, this is verifying the monad law using, I guess, going from the Kleisky laws back to the monad laws or something like that. Yeah, I thought, these constructions were kind of interesting, that you could sort of create. Oh, well, this is a negative one, I guess.
Mhm.
But like the one I was pointing at, 8.2, oh, I guess I passed it already. Where'd it go? Yeah. The product of two monads is a monad. Okay.
Mhm.
And then, yeah, this is something Sergey mentioned before,
Mhm.
that this is also a semi-monad. And oh no, I guess this is the one he was talking about before, that A plus F of A is a monad.
Right. But in general, the sum of two monads,
Plus.
not monad.
Right, right. There's 10.5. Okay. Hmm.
So
Yeah, so it's kind of like the reader wrapping a monad in a reader, in a sense.
right, and and he says he uses the flipped Kleisly trick in the proof, which again, I didn't actually follow the proof.
Yeah. But it's kind of interesting to know.
It's interesting to know, right? And it's nice to know that we could come back and consult these constructions if we ever needed to.
Right. So contrafunctor. Then, oh, I guess this is sort of the reverse of the one we were just showing, that if you have a functor, you can go this way, and if you have a contrafunctor, then you can put it on the left.
Mhm. Not too surprising.
Yeah, I guess. Yeah. Oh, here's one. I didn't look at the filterable
G
one
filter.
here. Contrapunctors. Okay. All right. Start getting more complicated, and I can't paraphrase them on the fly here.
Right. Mhm.
So exercises, I didn't do any of the exercises.
I'm afraid I
Maybe
did.
we did some before, but why monads must be contravariant functors. Sergey, can you summarize why? And is it just covariant functors, or do they have to be like strictly positive? Your mic isn't on. But maybe.
Yeah, well, so they don't have to be strictly positive. And
Just positive, okay.
if you take a look at the construction with contrafunctor, so h of a to a, that's not strictly positive necessarily,
Okay.
right? Because h of a is contravariant, so it could contain a in the negative position. Then
Hmm.
have h of a to a, which will have a positive positions, but not strictly.
Hmm.
positive.
Hmm.
So
Okay.
yeah, it doesn't have to be strictly positive, but it cannot have negative positions. And yeah, but and this is the, in my view, this is just kind of a no-go result where you cannot derive
Hmm.
any reasonable properties or monads that are contravariant.
Okay.
I mean, it's not there. In my view, it is more formal. But I always ask the question, can we have contravariant? For instance, filter. Well, you can have contravariant filter.
So if you ask the question, can monads have contravariant be based on contravariant functors?
Yes.
Right.
You
No,
can have
we can't.
contravariant applicative. You can have contravariant filterable. So can we have contravariant monads? And the answer is no.
No contramonads. So just as I should warn you, I need to leave early. This is another of those days when I have a second meetup scheduled right after this one. So I will have to go in about 10 minutes. Is 2 weeks from today good for the next meeting? 3rd of June.
Sure.
Anybody with a conflict?
I have a conflict on the 3rd of June, but
Oh, okay.
that's okay. I mean, if you guys want to continue on that.
Yeah, I also do. I think I'll be traveling that day.
Is the 10th of June any better?
Yeah, it's better for me.
Yeah. Anybody else? Okay, so let's say the 10th of June, and I will be on vacation for 3 weeks following that. So that might be our last meeting until July sometime. So if that sounds okay.
Sure.
When do you get back? Should we
I get back on
put
the
something
4th.
on the book? Well, I guess you'll be here on the 10th. So
Yeah, I'll be here on the
we can
10th.
plan the next meeting.
Yeah. We return on the 4th of July, so sometime after that. So yeah, and so do we want to tackle the parametricity for nested types, or do we want to head on to the applicative chapter from here? Any strong preference?
Oh, he's still sharing. Yeah.
Do you think we can cover the whole parametricity paper in one session? Seems like a pretty heavy slog there.
It's a heavy slog. We might not be able to cover it in any number of sessions. But I would be willing to start. I mean, I can read the first couple of pages without too much trouble.
There's a section where they introduced the left con extension. And I'm thinking, uh-oh.
Yeah, yes, I'm guessing it gets heavier going from there, but we could maybe go through the first few pages of it and see if we can get anything out of it. Anybody opposed to that plan?
I guess I wonder if this paper is too deep. I mean, we kind of switched to this one from the other one by the same authors, where, what was it? Something like initial algebra semantics is enough,
Yeah,
exclamation point. And that had a lot more like readable Haskell code in it, or Agda code, whatever. This one seems a lot more dense. And if we thought the other one was too dense, because I don't know why we switched. I think it was because we thought it was too dense. But we also switched because we thought this other paper talked about GADTs, and it's really more a negative result, saying that GADTs, you aren't parametric. So I wonder if we should go back to the previous paper. So maybe what we should do is do the applicative one next time, and I'll do some homework in terms of like comparing the two papers and seeing which seems more useful and approachable. But
Okay,
that's just my thought.
that sounds good. All right, so let's launch into the applicative chapter for our meeting 3 weeks from today. And I guess we can hop back to looking at the further developments section of chapter 10 for a few more minutes. Then I'll leave you early and look at the recording to see what I missed. How's that?
Okay.
Okay, we got a plan. So Pete, do you want to resume where we left off?
Okay. Sorry. Things have moved around here, so I got to get back to where I was. Oh, okay, good. More share. Right. So I didn't look at that much. I mentioned this one before, monads, effects, and runners. And here he talks about sort of coming up with runners in general. In some cases, you sort of throw in an arbitrary value. Like if you want a runner for option event, then you'll basically, the idea of a runner is you're going from the monoid on some type to that type. But some things like option, you don't have a value of that type. So you sort of pick one, 0 in this case, and then you can make that be your runner for option.
Right.
Seems a little arbitrary to me, but I guess it's application dependent. If that's, that kind of makes sense, that's often what you want to do. So
Right. It's sort of like you have a pointed int, as it were, and you choose the point on a case-by-case basis, whatever you need the default to be.
right. If you have option of a pointed type, then
Then it could be the
clean, because then you just use the pointer, whatever, pointed to one. And wait, did I miss something here? This is where Sergey begins to talk about, instead of having a runner of type M of A to A, might make more sense to go to another monoid, N in this case, because then you can kind of wrap things up more cleanly. So you go from an option to an either, and I guess the other way around, by throwing, either putting in appropriate information or throwing it out. In the case of going to an either, you sort of have some error string that you just kind of throw in if the option fails, which is probably often what you want. And yeah, as we were talking about before, the M. Kleisky category, they form, the Kleisky functions form a category, where identity is pure, basically, and composition is the Kleisky composition.
Right. And so in the third paragraph, Sergey says, functor M is a monad if and only if the corresponding M Kleisly category is lawful. This is a concise way of formulating the monad laws, and that's pretty concise.
Mm-hmm.
Yeah, and that actually works for a monad in any category, I believe, not just the types that we're looking at here.
Mhm.
It's entirely a categorical fact, I think.
Anybody want to say more about this?
About monad morphisms. It still seems like a rather advanced construct to me. So anyway, I'm afraid this is where I have to excuse myself, but I'll look at the recording and see what you all said and see you all in 3 weeks.
Thank
All
you.
right.
Okay. Bye.
Bye. Oh, it's gone.
Yeah, so a monad morphism is more constrained than a natural transformation because it needs to preserve the laws of the monad. And in fact, I give some examples and exercises where I show that certain natural transformations are not monad morphisms. Just as a kind of illustration, so that's, you might think something that is defined very elegantly and concisely, must be a monad morphism, but no, it is not. And so in other words, there are some laws that you need to check, and you need to verify that this natural transformation preserves the laws, and this is a very strong constraint, actually.
So you have identity law and then two versions of the composition
Yeah, well,
law,
the
right?
composition law most easily is in terms of
This
the
one.
classly functions. Yeah, I mean, this composition law is not maybe not very clear why that is important and why it's like that. But if you like think about the classly
mean, this
functions, then it's just yeah, this one. It's kind of composition is mapped into composition. And the classly compositions are even more like when you compose in the n monad, then it must be the same as when you first compose in the m monad and then you transform to n. So this is kind of preserving the composition. So you this is maybe more clear why this is a composition law.
Right.
And there are so this is kind of this is a concept that is used in a few places, but I'm motivating it by saying that if you want to run a monad into a value or into another monad in your program, then you want these laws, because then you can refactor your program. You can run parts and compose the results. And that's the same as if you first composed the monad things and then you run all of them. So if you want this kind of refactoring freedom, then you want this law. Now, it doesn't mean that you always must have it. And it doesn't mean that if some runner does not satisfy this law, then it's completely wrong. It just means that you shouldn't refactor your program. If you refactor your program, you might introduce a bug. So, for example, the runner for the state monad does not satisfy the composition law. And that means if you have a state monad program, you have to run it all at once. You cannot run parts of it and then compose the results.
Because the state has changed.
Yes, the state has changed. So you don't see that change when you extract the value out of the state monad. And so you must compose everything in the state monad, and then you run the entire big state transformation. Only then you get the right result. So this is, anyway, so formally you can see this by saying that you are violating the composition law by the runner of the state monad. So it's not a monad morphism between state monad and some other monad. Anyway,
So
I need to
basically,
drop
we
off
start
maybe
with
right now.
natural transformations, and then we
Yeah.
narrow them by adding in the identity law, and then one of these composition. But then it sounds like these composition laws can, in some sense, are optional. You can still do natural transformations or transformations without them, but when you have it, it's a nice property because it allows you to refactor, as you said, split stuff up. Okay. And then you talk about the category of monads and monad morphisms, which I guess we've seen in the category theory. Yeah. Okay. Anything else you want to look at here before we go? Kantism between the Reiner. Okay. There's some exercises here. Oh, I guess I looked at this exercise. M is a given monad, Z is a given type, and you have a given value M0. Even though they have the right type signatures, F is not a monoid morphism. And the way I did that was to say, okay, choose M being list, and M0, then, being I guess, it would be a list of Z's. So let M0 be a list of 3 Z's. If you apply this to pure, then you'd basically transform the 3 Z's to a list with 3 A's in it, with little a, because pure takes an argument. So you would like map across your Z's and just throw away all the Z data and just replace it with the pure value. And that list of 3 things can't be the same as the pure for list, which just creates a single element list. That makes sense. Okay, it's getting late and I think everybody's tired. Maybe we should wrap this up.
Yeah,
Yes,
sounds
thank you.
plausible. I'm just not quite following it.
Yeah.
Might help to write it up.
Yeah. I scratched something on my iPad, but so
So
hard
this
to get
function evaluates on the value m's. Oh no, it doesn't do that. What does it do?
which
Oh, okay. It lifts. All right. So what this function f does is to lift the given mapping to the monadic version and then evaluate it on the fixed value M0. Does that sound right?
right.
Yeah.
Well,
Okay.
right. So you F map the function you're given by M and then apply it to M0. Is that what you
Right.
said?
Okay. So it's the only, it does the only thing it could do, which is that. Yes.
418.
And this looks, as far as type goes, it looks like a monad morphism, and it's very simple to define, but it fails some monad morphism law.
Yeah. This is what I scratched, you know, so pure, okay, because I want that. Pure takes an argument and, you know, for like for the reader, just throws away the Z and yields the A. So
It's the
but
constant function.
yeah, for a given argument.
And a monad morphism would have to preserve pure.
Yes. So yeah, so if you stuck pure of A into F, basically you get that you're going to F map pure of A and then apply it to M0. Well, pure of A just basically throws away the Z part and just puts in whatever that constant A is. So if you take M as being list and M0 as being a list of, say, 2 Z's, then when you F map this function over that, you'll get the list with A in it. Whereas the pure for list would just be the singleton, the list with the one element, A.
Okay,
And so they're not equal.
that looks plausible. Cool.
But I didn't really look at B. I sort of did this morning. I don't know why. Just got curious. Yes, so here specifically, he's talking about the reader monad. That's where this pure of A came from. Right.
Mhm.
Well, what do you think? Keep going or come back to it? You only have 2 minutes. 1 minute. So why don't we wrap this up?
Yeah, thank you.
Okay. Thanks to Sergey and all of you.